In this section, we're going to talk about electrodynamics, so moving electric charges. In previous sections, we talked about magnetism, electrostatics, the process of a process and means of electrification, and we gave the unit for the electromotive force, electrons moving. We said that's the volt, the push or pressure through a conductor. So we're going to talk about electrons moving, electricity, electrodynamics here. So a couple definitions to start us off. Electrodynamics is just the continuous flow of electrons along the surface of a conductor. Assume a solid material for right now. Electrodynamics is the study of flowing electric current, so the study of electricity is electrodynamics. So what's current? Okay, we say that an object has an electric current when electrons flow along the surface. When electrons move in a direction away from a negative charge or toward a positive charge along the surface of a conductor, and electrons flow when there's a potential difference applied, when there's a difference in charge from one end to the other in a circuit. We refer to the potential difference, or the electromotive force, the force that pushes the electrons, as voltage, with the unit being the volt. Conductivity is the material's ability to transmit electrical current. A conductor transmits electrical current easily because that conductor will have loosely bound electrons in the valence shell of the atoms that make up the material. Said in another way, the electrons are free to move easily through the material. Quick kind of cartoon picture of what we're talking about, electrical current. It's okay to picture, for analogies and metaphors, other things beside this. My personal favorite for thinking about electricity is picturing water moving through a garden hose. You can sort of analogize that to help you. However, the truth is that electric current is a leapfrogging, a hopping of electrons from atom to atom to atom along the surface of a conductor. One electron hops to the next atom nearby, away from the potential difference, or toward the potential difference, however you want to think about it, giving that next atom an excess of electrons, which is then causing the atom to push off an electron to the next nearest atom, and so on and so on and so on down the line, like a leapfrog. All right, conductivity. So conductors, as we said, allow electricity to pass easily because of loosely bound electrons, and good examples of that are things like copper, silver, aluminum, brass. Notice they're all metals. Water is also a great conductor of electricity. Gold is a good conductor of electricity. Things that don't conduct are called insulators. They resist the flow of electricity, and if you're paying attention, the only difference that should be apparent here is that an insulator, like dry wood, plastic, glass, or rubber, have tightly bound orbital electrons, meaning they don't hop around easily, so you can't electrify them, or very difficult to electrify them. Semiconductors, and by the way, dry wood, to be specific, wet wood would conduct electricity, but that's not because of the wood, that's because of the water in the wood. So dry wood would not conduct electricity at all. In what I think about in that is I think about lightning striking a tree. Lightning can strike a tree and move through the tree, but it's moving through the water in the tree, not the wood of the tree. Anyways. Semiconductors. Semiconductors allow electricity to flow, but only under certain conditions. For example, if they have a very specific amount of voltage applied, or if there's a specific pressure on the material, if there's not just normal room pressure, but a higher pressure, or if the material is very hot or very cold, or if a certain wavelength of light is shone on the material. Semiconductors are sort of special because they only allow electricity to flow under certain circumstances. We use semiconductors in all computer chips, your cars, your phones, your computers, all these electronic devices all use semiconductors nowadays. Okay, electrical current. So we learned current is the flow of electrons along the surface of a conductor. So mathematically, we can say that the rate of flow of electrons is current. So we like to use, we could have picked anything. We could have picked tens of electrons per nanosecond, but the easy unit to use is electrons per second. So, or coulombs per hour if you've got large amounts of current flowing. But electrons per second is a pretty usable term, a usable one for us. We like that. We say that the unit is the ampere or amp, capital A or I, defined as 1 coulomb per second. Okay, so 1 amp of current is 6.3 times 10 to the 18 electrons moving past a certain point. Pick any arbitrary point and then measure how many electrons move past it per second. And if you're flowing at a rate of 6.3 times 10 to the 18 electrons per second, that's 1 amp of current. If you are remembering, coulomb was the unit for static electric charge, so that amount of charge not moving is a coulomb. That amount of electrons moving past a point in over 1 second's time is an amp. In radiography, the amp is a large unit. We'll learn some rules later on about Ohm's law and things like that, how voltage, amperage, and resistance play together. But one thing that we'll need to learn is that in an X-ray machine, to create X-rays, and in upcoming lectures we'll talk about that, but to create X-rays, we need to make high voltage. We need to make extremely high voltage. We access at the wall for our electric devices, things we plug into the wall. We access 110 volts, 220 volts, but that's it. In order to access 100,000 volts or more, slightly more, slightly less, but in order to access volts in the magnitudes of hundreds of thousands, you'll have to have low amperage. So we don't need a lot of amperage. We don't need a lot of current flow. We don't need a lot of electrons moving to have to create X-rays. We need a high potential difference. We need to push those electrons very fast. So because of a thing we'll learn later called Ohm's law, with high potential difference, you get lower amperage. We use units like the milliamp when we talk about electrons moving through our X-ray equipment. Common milliamperage settings for your X-ray equipment include 50 milliamps, 100 milliamps, 150, 200, 300, and all the way up through 1,000 in the newer types of equipment. A milliamp is just 1/1000th of an amp, or 6.3 times 10 to the 15. 10 to the 15 versus 10 to the 18 is 1,000 times smaller. So we use the milliamp in setting X-ray technique. We'll, from here out, probably just refer to it as MA. To give you a reference about, how effective this is, it takes only 0.6 milliamps, not even a full milliamp, to cause death if a human's exposed to 0.6 milliamps electrons moving through the body. And in radiography, for a more useful unit, we want to know, for a total X-ray exposure, how many electrons were used during that exposure. How much total electricity did we use? For that, we want to know the mass number. Mass, MAS, mass, takes into account how many electrons you used, the MA, and how long you used it for. How long was the exposure being done for? So we take the milliamperage number and just multiply that by time in seconds.